Hello and welcome to the logic of it all. In this video, we will talk about finite state machines and more specifically, finite state transducers. And as always, let's start with a little bit of motivation. Finite state machines are used in many different applications as a mathematical model for computation. And here are listed some of those that include things like natural language processing or video game programming or hardware design and so on. Now let's start with a very simple example, a coin-operated turnstile. Now I use a coin operator, but you can think of, a turnstile gate that operates with, credit cards or anything like that. And we know what they are. These are the gates where you either scan your card or you insert a coin and then the gate opens, you go through, then it gets locked for the next one and so on. Now, if you think about this, we can imagine that the turnstile gate can be in two possible states. It's either that it's locked or it's unlocked. Now, through this diagram, you see that if the turnstile is locked and you insert a coin or you scan your card, then what happens is that the machine transitions from the state of being locked through this arrow, it transitions to the state of unlocked. Okay? And on the other hand, if you are in the state of locked and instead of inserting a coin, your interaction was to push the turnstile, then you stay in the same state, which means that the turnstile remains locked. So your transition will be from this state to itself, which is represented through this edge here that you see, goes from the state of locked to itself. Now, on the other hand, if you are in the state of unlocked, which means that you have inserted the coin previously, and the next move is pushing it, then what happens is that obviously it opens and you go through it, but then the state changes to locked again, because now the next person is coming in and it's supposed to be locked until they insert a coin and so on. So this arrow here represents that scenario where the gate is unlocked and you push the gate and you go through it, and then the transition happens and it goes back to the state of being locked. And finally, if you are in the state of unlocked and your action is inserting another coin, then the gate remains unlocked. Okay? So this is a simple diagram that shows how the turnstile operates given your actions, and we see that we only need two states to represent this, the state of being locked and the state of being unlocked. Now later on when we talk about these machines, we will see that these states can be thought of as memory. So the state of the memory. So the machine needs to remember whether it's supposed to be locked at the moment or unlocked, and then depending on the actions, it may need to change its state from locked to unlocked and vice versa. Now, this is a very simple example, but it's a very useful way to start talking about this. And another thing that we can do here is we can summarize all of that, all of what's happening in the diagram in this table. So you see on the first column we have the state, the current state. It's either locked or unlocked. Then on the second column we have the input, what the user, the client does. And we have two possibilities. It's either that they insert a coin or push it. And similarly for the unlocked situation. And then depending on the combination of the current state and the input, we are going to have the next state that the machine ends in and the output, what happens as a result of that action. Okay, so let's go through a few of the, we have only four possibilities, so let's go through them one more time. So if you are at the state of locked currently and your input is inserting a coin, then the next state will be unlocked, and that should make sense. And the outcome of doing this is that it unlocks the turnstile so that the customer can push through. On the other hand, if you are at the state of locked again, but your input this time is push, so the turnstile is locked and you push it, the next state, the state should not change, it shouldn't open, so it remains locked and nothing happens. On the other hand, if the current state is unlocked and you insert another coin, it remains unlocked and nothing happens. And finally, if you are in the state of unlocked, so the gate is open and you push it, what's going to happen, the output is that it allows the customer to push through and then it locks the turnstile for the next customer, and which means that the next state is going to be locked. So that table summarizes all the behavior that is expected from the diagram above. And as we will see later, because of in order to make this information more clear, we are going to split this table into two tables, but we will talk about that in later videos. Okay, so now that we have an intuitive understanding of finite state machines, let's talk about two different types that we are going to investigate in these videos. The first one is a type of finite state machine that receives an input. In the previous example, the input could be either a coin or push, and it produces an output. Okay, in those cases, we call the machine a finite state transducer. Another type of finite state machines that we will talk about in the next videos is what's called a finite state recognizer or acceptor. Now here, the machine accepts an input, but it doesn't produce any output. But after inserting a sequence of inputs, it either accepts or rejects that input. Okay, so that's why it's called an acceptor or a recognizer. And as I said, in this lecture, we are going to focus only on the first one. In later lectures, we will talk about the acceptors as well. And to be able to talk about these concepts more clearly, let's define some terminology. So we talk about inputs, and we have a set of possible inputs, and we call that the input alphabet. Now, in the previous example with the turnstile, our inputs were either a coin or a push, so that's our alphabet. But for simplicity, usually we use things like 0, 1, or the letters in the alphabet and so on as our input alphabet. And if the finite state machine generates an output, then we need an output alphabet. And that can be either the same as the input alphabet or it could be a different one. So the set of symbols that the machine generates as output is the set of all possible inputs, I should say, is called the output alphabet. And in a lot of applications, again, as we will see here, we are going to use the binary set 0, 1 as the output alphabet, and sometimes it could be the letters in English alphabet and so on. Now, usually we don't design these machines for a single input. Again, if you go back to the turnstile example, we don't have just one customer either inserting a coin or pushing. What we expect is a sequence of customers where they insert the coin and then push, and then the next one comes in and so on. So we are interested in studying these machines when we have a stream of inputs, and that's called the input stream. And as a result, the machine is going to create a stream of output symbols that we call the output stream. Okay, remember that we are talking about finite state transducers, so they have outputs, right? Later, when we talk about acceptors, there is no output, so there is no output stream either. Now, as I said, in this video, we are going to look at finite state transducers. In later videos, we will talk about finite state recognizers or acceptors. The difference is going to be that the second type, the acceptors, they don't generate any output, but after the stream ends, they either say this stream is accepted or not. Now, I will talk about this in more detail next time, but you can imagine you have a programming language and then you have a set of rules for the names that you are allowed to use for your variables, right? All programming languages have some restrictions on that. Things like you are not allowed to use special characters, some specific characters, or the name must start with either a letter or a digit, and so on and so forth. So you can imagine a finite state acceptor where it reads the entire name that you have chosen for your new variable and either says yes, this is according to the rules, or no. So it either accepts the input stream or rejects it. And as I said, we will talk about this in more detail in later videos. And finally, there is a third type that we do not talk about here, but I just wanted to draw your attention to it. And these are called finite state generators, where they don't receive any input, but they produce outputs. And we will not talk about this third type in these videos. All right, now here's my first example with more detail. So our input and output alphabets are the binary symbols 0 and 1. And we are going to look at a machine, a finite state machine, that has two states, S0 and S1. And here's the behavior that we want for this machine. If we are at a state S0, and the input symbol that we are reading at the moment is 1, what the machine does is that it changes its state to S1 and outputs a 1. Second case, if we are at the state S1, but instead of a 0, the input symbol that we read is a 1, what the machine does is that it stays at S0, so it doesn't change the state, but it still outputs a 1. Third case, if we are at the state S1, and the input symbol that we read is a 0, what the machine does is that it goes back to state S0 and outputs a 0. And finally, the last piece of information that we need to be able to understand the machine completely is the fourth possible case where the machine is at state S1 and the input symbol is a 1. Now what the machine does in this case is it stays at S1 and it outputs a 1. So these 4 lines explain how the machine works in all possible scenarios. Now what we can do is we can summarize all of this into a diagram that is a directed graph that looks like this. Okay, so this is our first state, S0, this is S1, and the transitions that we had was if we are at S0 and our input is a 0, what we do is we output a 1, so that's what this bit here means. On input 0, we output a 1, and we transition to state S1. So that's the first line. Then if we are at S0 and the input that we read is a 1, we output a 1 and we stay at S0. Now on the other hand, if we are currently at S1, we are here, and the input symbol that we read is a 0, we output a 0 and go back to S0. And finally, if we are at S1 and we read 1 as the input symbol, we output a 1 and we stay at S1. So the whole description that was on the previous slide is summarized in this directed graph with edges labeled like that. So this is called the diagram of the finite state machine. Now, as I said, we are more interested in the behavior of these machines on a sequence or a stream of inputs. So that's the next part of this example. So what we want is we want to know what happens if the input stream is this. So the first input symbol is a 1, then another 1, then a 0, then a 1, and then the final input symbol is a 0. So we want to know what the behavior of this function is. Now to be able to do that, we need to know which state we should start from. And that's a specific state that is called the initial state. And this arrow here represents that. So we know that S0 is our initial state, which means we assume at the beginning we are at the state S0, and then we read the first symbol 1. Now, if I'm at S0 and I read a 1, you see this is the arrow representing that. So what I output is a 1. So the first output symbol is going to be a 1, and I stay at 0 because that's what the arrow does. Then I read the second input symbol, which is another 1, and then the same thing happens. I output another 1 and stay at S0. Then I read the third input symbol, which is a 0. Now with a 0, while I'm at S0, with a 0 I output another 1. So that's the third output symbol. And the arrow tells me that now I transition to S1. So now my current state is S1. Then I read the fourth symbol, which is a 1. And remember that now I am here at S1. And when I read a 1, first of all, I output another 1. And the arrow, the edge, tells me to stay at S1. So I'm still at S1. And finally, I read the last input symbol, which is 0. And remember that I'm still at S1. So when I read a 0, I output a 0 and transition back to S0. So the output stream, given this input stream for this finite state machine here, is going to be 1, 1, 1, 1, 0, and I end up at state S0. Now, a little bit more detail about the transition diagram. So as we said, for a transducer, a finite state transducers diagram, transition diagram, is going to be a directed graph, as we saw in the previous example, where the vertices, each vertex is one of the states, and each edge represents a transition or a behavior, the behavior of the machine on that given input, given that we are at some specific state. So for example, if you look at this part over here, if we are at S and the input symbol is an A, we output a B and we transition to this other state S prime. So that's how we understand these transition diagrams. Now here's another example. This time my finite state machine has 3 states, namely S0, S1, and S2. I know that S0 is my initial state because of this arrow on the left side that goes from nowhere to S0, so that means start from S0. And then we have the other edges that tell me how the transition works given that we are at S0, S1, or S2, and the input symbol, which is either 0 or 1. Now, the question is, if my input stream is 1, 0, 0, 0, 1, what would be the output stream and what is the final state that I end up at? Okay, and what we need to do is, starting from S0, we need to consume this input stream one symbol at a time, and then follow the edges to go to the next state, and so on and so forth, and keep track of the output symbols at each step. So initially we are at S0. The input symbol that I read is a 1. This arrow over here tells me that I need to output a 0. So my first output symbol is a 0. And I go to S2. Now I'm at S2. The next symbol that I read is a 0, second input symbol. If I am at S2 and I read a 0, I output a 0, and I transition back to S0. Now we have read 2 of the input symbols, so we read the third one, and remember that now we are at S0. So I read a 0, and this edge here tells me that, first of all, I need to output a 1, and I need to transition to S1. So now my current state is S1, and I am ready to read the next symbol, which is another 0, and this time I'm at S1. So this edge here tells me that I need to output a 1 and transition to S2. So now we are at S2, ready to read the next input symbol. which is the final symbol, and that's a 1. And this arrow, this edge here, tells me that I need to output a 1 and stay put at S2. So this string 00111 is my output string, and my final state is I end up at the state S2. Now here's another example. Let me clear things up a little bit here. So same machine, but this time a different input stream, namely the stream is 01010. So again, we start from S0 because we know that's our initial state, and then we consume the input one symbol at a time. So 0 is the first symbol. I output a 1 and go to S1. The next symbol is a 1. I am at S1. With a 1, I am supposed to output a 0 and stay at S1. The next symbol is a 0. I am at S1. With a 0, I output a 1 and transition to S2 this time because of this arrow. I'm at S2. The next symbol that I read is a 1. At S2 with a 1, I'm supposed to output a 1 and stay at S2. And finally, the last symbol that I read is a 0. I'm still at S2, but if I read a 0 while at S2, I need to output a 0 and transition back to S0. So my final state is S0.